All right, so let's just get right back into it. I'm going to try not to do too much repetition between these lectures. Actually, I'm kind of doing this series sort of all in a row because I understand this proof today, and if I wait too long, I'll have to go back through it, months from now. But and then I'll just sort of start over. So to me, there's less motivation to double back. On the other hand, since I don't know the order that people would be watching this or how much time they take in between, it is worth always starting with a quick rehash. But in this case, let's just stay tight to the story, right? Ultimately, this is the monster we're dealing with. In fact, this is so important, I'm going to take a picture of it, right? And I'm going to take that picture and put it on the other pages so we can keep this expression with us, because we're trying to figure out all the parts to this expression, right? In order to solve this, I need this, this, and this. Now, these two are the same, so I really just need this, and I execute this guy twice. I do want to start by executing this step here. It's actually much more confusing than it looked. I didn't appreciate how confusing it was until somebody actually raised it in the comment section. I just took it as obvious, but it's not obvious. It's a notational step that involves this symmetrization definition. And I was surprised when I worked it out what I found. So literally, if you were to do this, if you were to substitute for this right into this expression, you would think that you would get this expression or the equivalent back out. So let's do that. The definition of this antisymmetrization, put it in here, and let's figure out what we actually get. So the first step is the literal replacement for this here. I guess I should make it look like that, right? And the literal replacement is you would take these three indices and do all possible permutations. So there's 6 possible permutations to these 3 indices. However, all connections in general relativity are symmetric already on B and C. So, for example, this permutation BCD is equal to CBD. So, and likewise, CDB is equal to DCB, and DBC is equal to BDC, right? I got all that right? So there's a factor of 2 in front of each of these, which I pulled out right here. You divide by 3 factorial because there's 6 total permutations. So this ends up being a 1/3, right? A 1/3. So let me erase that, right? And this ends up being a 1/3. So the literal replacement for this is 1/3 times this. And, okay, now if you look at this, right, you have this guy here, right? So now imagine that we put a VD, VB, VC here, right? So this term here is just one of you can imagine contracting into these 3 V's, any one of these terms. In fact, consider the first one. This one here is literally the same as that. I've changed it to my favorite notation, right, where it's a little easier than writing all these partials on it, so I did it this way. But this contracted into that is literally what this is, right? So there's a 1/6 here, though. So this would be 1/3, right? This would be 1/3 times this times that, which is twice as much as that term. But this happens 3 times, right? Now, these two here, the numerical value of this contracted with this is identical to this contracted with this and this contracted with this. These are all dummy indices, right? This D and that D, I could switch that to I could switch this D and this D to a C, and this C and this C to a D, and it would equal the same term, right? This is really 3 times this, right? So if I basically could make this equal to 3 times this one term. And as 3 times this one term, then I have this 1/3. So this right here, as written, literally equals this term right here, right? But the problem is that there's this 18 here. And what it looks like actually happened, I mean, so if I literally take this, the definition of this, if I literally take the definition of this as I wrote it out here and put it right in here, right, I would end up with a 118 times a 1/3 times this. So I'd end up with like 154 multiplied by this guy right here, right? And that's not what they've done, right? This is certainly not equal to this. So what I think has actually happened is that they've used some unusual notation here. They have actually done something a little different. They've used this antisymmetrization in a way that's not quite correct. What I've surmised is this is what they mean. That's why I put a little exclam, because it's as far as I'm concerned, it's not standard, right? I mean, this is only symmetrized in a true sense if you already know that this guy here is symmetric in B and C. But true symmetrization notation should apply to any tensor, regardless of any pre-existing symmetry. So this definition, and plus it's also missing the coefficient, right? It should have a 1/3 there. But they've already accounted for that 1/3 in this going from 6 to 18. So now if you substitute this into here, you end up with 3 times that term. So you divide by 3, which is where that 18 comes from, and now this literally equals that. So this is a warning that this is a bit of a non-standard notation. So as we flow through the rest of the paper, for example, in particular, later on when we start seeing it everywhere, understand that this is not the totally symmetrized thing, right? This doesn't become 1/9 times the symmetry here. This is just 1/3 times this factor right here, right? That's what it is. So that's an important point to keep in mind as we go forward. By the way, if you go to this paper, this second paper, Physical and Geometric Interpretations of the Riemann Tensor, and we're studying this paper here, don't get me wrong, but if you go, this paper here does a similar proof. And when they get to this spot in the proof, right here, they actually introduce this symbol right here, this gamma tilde symbol, which they define this way. They don't attempt to use this standard antisymmetrization notation. They actually define a symbol that just has these 3 terms in it. And they end up with, I think they end up with a factor of 2 difference. Actually, no, they don't. They end up in the exact same place. But notice they use their symbol here, which literally means what I just wrote. Yeah, so I think I'm on the right track about the way this notation was handled. The other paper has this formula and definitely goes to this formula, but uses this definition. And I think they just slipped in this sort of non-standard definition. But when we see this, for the duration of this paper, we've got to think this, not the full true symmetrization. Yeah, these two come from the second paper, so if you want to double check, go ahead. Okay, so let's move on. All right, so the last lesson we ended up on this line, and I think I pointed out that I guess we have XA P plus lambda. We really have to understand this deeply. You can't let this slip by, and so I want to emphasize it. I don't know. Maybe this is redundant after all. But look, the notation P plus lambda, that is telling us that we are going onto the surface of this sphere Sn minus 1. All these points are described by P plus lambda. So the point is, the thing I want you to know is that if this is that sphere, right? If this is that sphere on Sn minus 1, and here I'm drawing it like a child, but this is that sphere. We know that there's a coordinate system on that sphere called theta I. So every point on that sphere has coordinates theta I. Now, let's not worry about coordinate charts and whether or not you can cover the whole sphere with one coordinate. But given it's any given chart, it has a complete nice set of coordinates, theta I. And we know this because it's a manifold. So if you are a point that's accounted for in this nice notation p plus lambda, if you are a point that satisfies this rule, you have coordinates theta I as a point. And you could actually sort of do it this way. You could write theta I is the coordinate functions for any point that satisfies this p plus lambda condition. And this function returns the ith theta coordinate of a given point on the sphere. That's what this means, right? And we just do a shorthand and we write this, right? If you're not on the sphere, you don't have theta coordinates, right? It's as simple as that. So basically, we should be able to write xa as a function of theta I here, right? Now, what about the right-hand side, right? The right-hand side, lambda is just a number. And remember, VA is the vector at the point P such that that vector launches a geodesic that hits some point P plus lambda that is on the sphere, which has coordinates theta I. So clearly, as you change this vector VA, you land at a different point on the sphere and you get a different point theta I. And each of these vectors, no matter what they are, they always define, these are unit vectors, right? They always define one point on this sphere Sn minus 1. So the vector itself is a function of what point it's targeting. And that's why we can write VA of theta I, right? The vector is defined by the point it's targeting. There's a temptation to think of it the other way around. The point is targeted by the vector because the vector kind of launches the geodesic, right? But what you're really doing is you're solving a boundary value problem where you know the point you're after, right? And you know the point you're starting, and you're choosing the vector such that you land at that point. So we're thinking the vector in terms of theta I, and that's true for all of the other things. So minus lambda cubed over 18, that's a constant. This thing here, this partial d, I almost hate to write it because it's so weird, but this partial d gamma a, b, c, that's evaluated at the point P. And then, of course, you have Vd of theta I, Vb of theta I, and Vc of theta I, right? So this is a function of theta I, right? And it is only those points, its coordinates in the manifold M, right, of a point on the manifold Sn minus 1. And that is the definition of the transfer function. This is the transfer function, right? The transfer function is the thing that goes from the manifold Sn minus 1 to the manifold M, right? It's xa of theta I. So we have now found the transfer function. Now, the problem, of course, is we don't really understand these functions very well, right? But it turns out we're not going to need to. But this guy is the transfer function. And the reason that's important is because once I have this guy, I can take its derivative with respect to theta I, right? So if I take the derivative of this with respect to theta I start getting what I'm looking for. I start getting what I need to, I calculate this, right? That's what this means. What all that I've just said was to show what this line means, right? This is, I'll just fill it in, right? X of A of theta I, right? V of A of theta I. And this is of theta I, right? And this is dVc of theta I, d theta I. So all this makes perfect sense. Now, the reason this 118 goes to a 1/6 is by the product rule, right? If I go down here and I take the derivative of this, which is, well, we could look at it right here where it's a little cleaner, right? Actually, why don't I do that? Where here I've kind of written in the way I did it before. Notice when I say theta I here, I mean, it's a full set of coordinates, right? The I is just a little superfluous. I probably should have just left the I off. It's a full set of coordinates. If the fact is because they're arguments in these functions, they don't count as real indices. The only indice that matters here is a, right? The only thing that survives here is a. Everything else is a dummy index. And the i's aren't even dummy indices. They're just placeholders to remind you that we're talking about theta 0, theta 1, theta 2, theta 3. That's what literally should be in each of these things, is this statement. Okay, but the point is that when we take the derivative of this with respect to theta I, where now all of a sudden I does matter as a coordinate, we're going to do it 3 times. The product rule is going to blow this thing up 3 times with, this is a constant. So it's the derivative of that with respect to theta I times those 2, plus the derivative of this with respect to theta I times the 2 outer ones, right? Plus that one times a derivative of these c with theta I times those 2. But that's all the same, so you add them up, so you get a factor of 3. And that factor of 3, when you take the derivative, that's a real factor. So it comes out here, this becomes 1/6. And that's the 1/6 you see right here, right? That's that 1/6. Okay, so that explains this formula, right? This formula is derived, this derivative is derived that way. But we got to remember, this guy here stands in for this strange thing here, right? That's what this is, right? This is the definition of this guy in this formula right there. So don't make the mistake of substituting the full symmetrization in there. Okay, so we made big progress. I took that picture of this formula, but they repeat this formula on this page anyway. But this and this we now know. It's this thing right here. What we've done, though, is we're looking a little bit ahead, and we've replaced this with theta, right? Because remember, if you're on p plus lambda, you are theta. So we're thinking that in terms of theta, but it's the same thing, right? And we now know how to calculate this and how to calculate that through this formula here. So now we have to work on this, which is what this is all about. And they say it's a bit easier. I don't think it's easier or harder, but it is a very straightforward expansion. No derivatives required, right? So the value of the metric, remember now, this is the metric on M, right? This is the metric on M. So the value of the metric on M evaluated at a point that's on the sphere is the metric evaluated at the point that's sort of the center of the sphere where all these geodesics emanate. The geodesic length times the first derivative of the metric evaluated at P. So this is weird. We got to kind of figure out what the heck they mean by that. And the same thing is, and it's a second derivative term, right? This is standard Taylor expansion, except again for their weird notation, which is not making this any easier. What they mean here, first of all, GAB is a function on the space-time M. So if X is an element of the space-time M, GAB is a function on X. It exists everywhere, including points that are on the sphere, which we would call X of P plus lambda. That would be the coordinates in M of a point on the sphere Sn minus 1. However, P is not just any point. P is the central point, right? P is the central point. So this isn't really like the derivative of some function of P with respect to lambda. That doesn't make sense, right? What it is it's what it's supposed to represent is lambda is a parameter that describes the length along a geodesic, which is a path in M, right? So lambda is some parameter that goes along this length. Well, GAB is a function of lambda through the fact that it's a function of X, and now we're going to force X to be a geodesic path. So we have GAB along some geodesic path X, which is a function of lambda. So now I can take this as a derivative with respect to lambda, and then I can evaluate that at P, which would essentially be at lambda equals 0. Usually the point P would be where this parameter length is 0, right? So a better notation for this would be, a better notation for that would be partial GAB, right, as a function of lambda evaluated at P, right? That's what they mean by that, right? So this is, and they're not too far off. It's just, I guess what they're trying to say is this GAB partial GAB partial lambda evaluated at P. So that P they're trying to call this thing the function, and that's the argument of the function. But the fact that this P is above this line kind of associates it with just the GAB, which is not really correct. Because the P is a fixed point. It's not a variable point. It's not an argument. It's not a general variable being fed to GAB. It's a fixed point. And therefore, GAB at a fixed point is a constant, and a constant, the partial derivative of a constant with respect to anything is 0. So you would literally take that to be 0. Anyway, but if you take it to be this and realize that the metric is a function of space-time, there's a path in space-time that's parameterized by lambda, ergo, through the chain rule, the metric is a function of lambda. I can take that derivative if I know the metric through the entire space-time M, right? If I know the metric, which I presume to do, right? We assume that we know that. Then I can take this derivative, no sweat. And then once I take that derivative, I have a partial derivative on M, and I can evaluate it at P. And that's what that means. Worth talking about because it's confusing notation. And this sort of flows through the entire analysis here, right? This becomes at P, right? This becomes at P. This becomes at P, right? And this becomes at P, right? So that's evaluated at P. That's evaluated at P. That's evaluated. Actually, this whole thing here is evaluated at P. In fact, I think it's time to actually execute this derivative right here. Actually, both of them. We need to understand how to literally do this with the parameterization. I think we did this in a previous lesson too, but it's worth reviewing, so let me write it down. So we know that GAB is a function of a geodesic path given by XE of lambda. Ergo, the partial derivative of GAB with respect to lambda is GAB with respect to XE times G times the partial derivative of XE with respect to lambda, right? So that's what this is right here, right? This statement here is this right here using this other notation for, using the shorthand for this, where you would write the partial E, G, A, B, which I would prefer to be G, A, B, E, like that, okay? So then the second one is just an application of the chain rule twice, right? If you go through this exercise twice, you end up with this expression, which has two partials of GAB multiplied by two partials of dx d lambda. And then this one becomes the partial of GAB multiplied by the second partial of dx d lambda, right? And then we start applying the normal coordinate rules, right? These guys, where this is 0, which also means, since the connection is 0 at P, right, we also know that G, A, B, C is always going to be 0 at P, right? And so that means this term goes away, and that is 0, so that term goes away. So you're only left with this second term here. And that's what this is, right? That's what that is. And so we have calculated now the value of the metric only at the points on the sphere Sn minus 1. So in some sense, we actually have GAB as a function of theta in principle, right? Because these guys, every point on that sphere has a theta coordinate, right? We would now have to, now we make our replacement, this replacement here, right? Where we define, this launching vector is literally defined by this expression, right? dxa d lambda. That is the tangent vector of the geodesic given xa of lambda. That geodesic, partial lambda, that is the definition of the tangent vector at P, right? This is all at P. So that's in principle a function of theta. That's in principle a function of theta. And so everything here is in principle a function of theta. This is a constant, right? Because it's evaluated at p. It's the second derivative, GAB, I guess you would go dc, right? That's what that is. And that's important, right? We're gonna go into this notation heavily soon. So now we have this function as well, right? We have we've calculated this guy, and it equals this thing, and it's also a function of theta. And so now we have all three parts. We can calculate this. We've already done this up here, right? We've kind of worked through that with the caveat about how that's defined, right? And that are the same, so we do it twice, but with a different index for the derivative, and then we substitute this in for here, right? So the next step is going to be literally executing this guy, substituting that right there, right? This and that, that's for substitution number one, and then this and that is substitution number two. They're identical except for the I here and the j here and the j here and the I here. It's the only difference there, right? And then for this, we substitute this, right? And then we were on our way. The caveats I'll keep reminding you about is one, the substitution for this term is a little non-standard, and we've talked about that. But also, remember, I'm telling you that this term is zero anyway, right? And it has a big effect, right? I mean, if that term is zero and that term is zero, like I claim, this product is going to be a lot easier to calculate. Okay, so in our next lesson, we're going to start here, and we're going to work through to get to here. There's at least one warning that we have to cover in that analysis, and then ultimately that will allow us to calculate this guy, which is the metric on Sn minus 1. So that's a function of theta, right? Sn minus 1's coordinates is a function of theta, but we now know that I should write this up. This is actually theta. This can be replaced by theta. This is a function of theta. That's the metric on Sn minus 1, whose coordinate system is theta. And this, of course, is theta, because anything that can be written as p plus lambda has a coordinate theta in Sn minus 1. So all these derivatives make sense, right? If I take the derivative of v with respect to theta, v is a function of theta. It's that launching vector, right? That initial condition. The shooting vector, if you ever did partial or differential equations, linear, if you ever did numerical analysis, numerical differential equation solutions, there was this sort of shooting vector where you could slowly change the initial derivative at a point until you met a boundary condition. These guys are functions of theta. That's a constant evaluated at p. This is evaluated at p too. Make no mistake. Right? This thing here is evaluated at p. That's evaluated at p. That's evaluated at p. Right? And everything else remains as a function of theta, I think. Okay, so we'll do this analysis. I said I wasn't going to do a lot of review this time, but I kind of did, I guess. But we did cover some important idiosyncrasies of the proof, right, about this and some other things. But next time we will actually kind of work through this algebra. The alerts for next time is this stuff right here. This is also a non-standard. If you want to work ahead, be careful. This is the non-standard thing that we have to deal with. They have this definition down there that they claim helps, but I don't think it does. And so we have to go through that. And then this process is very complex and very delicate, in my opinion. And we'll go through that.